Hello, I am the instructor, Wang Shengda. In this lesson, we will learn the basic concepts of crystals. Through this lesson, you will master the basic concepts of crystals, including crystal, single crystal, polycrystalline material, and unit cell. You will also understand the characteristics of polymer crystals. You will be able to determine the type of crystal based on unit cell parameters. A crystal refers to a material whose constituent microscopic particles, such as atoms, molecules, or ions, are arranged in a regular, periodic pattern in three-dimensional space. Most solid materials in nature are crystals. For example, sodium chloride is formed by the regular, periodic arrangement of sodium and chloride ions in three-dimensional space. Dry ice, or solid carbon dioxide, is formed by the regular, periodic arrangement of carbon dioxide molecules in three-dimensional space. Crystals are classified into single crystals and polycrystalline materials. A single crystal is a crystal in which short-range and long-range order extend throughout the entire crystal. A polycrystal refers to a crystal composed of many single crystals with different orientations. The opposite of a crystal is an amorphous material. This material has only short-range order but lacks long-range order, or even any order at all. An amorphous substance exhibits no order. A space lattice refers to the abstraction of the constituent points of a crystal into geometric points. This lattice is formed by a collection of equivalent geometric points. Each point in the lattice represents the structural unit of the crystal. The crystal structure can be expressed as follows. The crystal structure equals the lattice plus the structural unit. A unit cell refers to the parallelepiped in the space lattice representing the three-dimensional space. These parallelepipeds are identical in size and shape, representing the fundamental repeating unit of the crystal structure. The smallest unit with a periodic arrangement in three-dimensional space is the unit cell. Unit cell parameters refer to the 6 parameters that describe the unit cell structure A, B, C, alpha, beta, and gamma. These 6 parameters are the lengths of the 3 edges of the parallelepiped, also known as the crystal axes, and the angles between them. Based on their geometric symmetry, crystals can be divided into 7 crystal systems. These systems include the cubic system, where the 3 edge lengths are equal and all 3 angles are 90 degrees. Tetragonal system, where 2 edges are equal and all angles are 90 degrees. Orthorhombic system, where the 3 edge lengths are different and all angles are 90 degrees. These 3 crystal systems all have angles of 90 degrees between their edges. Additionally, there are the trigonal, hexagonal, monoclinic, and triclinic systems. A lattice defect refers to a discontinuity in the periodicity of a space lattice. As shown in the diagram, the white circles represent the ordered particles in the crystal, while the black circles represent impurities. Some particles in the material do not participate in the crystal formation. The presence of impurities, the participation of impurities in crystal formation, or dislocations in the lattice all constitute lattice defects. Next, let's learn about the characteristics of polymer crystals. In polymer crystals, the periodically arranged points are not whole polymer chains, but rather one or more structural units. In this direction, atoms are connected by chemical bonds, while in the other 2 directions, only intermolecular forces exist. In the polymer crystal system, anisotropy occurs due to long chains, so the cubic system does not appear. In other words, polymers only have 6 crystal systems. Moreover, few belong to higher-order crystal systems. Most are primary or secondary crystal systems. Polymorphic phenomena refer to when the same crystalline polymer exhibits multiple crystal forms. For example, isotactic polypropylene commonly has 3 crystal forms: alpha, beta, and gamma forms. The number of chain segments and the unit cell size in these crystals are different. The corresponding melting points of the materials also differ. Heterogeneous polymorphism refers to the phenomenon where different structural units can substitute each other in the lattice, or different structural units can be arranged in the same lattice. For example, the 3,1 helix of polypropylene and the 3,1 helix of poly-1-butene can form a eutectic. Polymer crystalline structures can undergo mutual transformations under different conditions. For instance, the stable crystal form of polyethylene is orthorhombic. However, stretching can transform it into triclinic or monoclinic forms. The stable crystal form of polypropylene is monoclinic, but changing the temperature, pressure, and adding nucleating agents can alter the crystal form. Due to the inherent inhomogeneity of polymers and the high difficulty of molecular motion in polymers, the crystals formed by polymers often contain more lattice defects than those formed by small molecules. Therefore, polymers almost never exhibit 100% crystallinity. The so-called crystalline polymers usually have both crystalline and amorphous phases coexisting. In this lesson, we mainly learned about the basic concepts related to crystals, single crystals, polycrystals, amorphous materials, space lattices, unit cell parameters, crystal systems, and lattice defects, as well as the characteristics of polymer crystals.